So hopefully you can hear me. I'm Nick New. I'm CEO of a company called Optalysys from the UK. We're here today because we believe in the blockchain's potential to transform the way people interact with the web. But for it to reach true mainstream adoption, we have to solve the challenges around privacy. At Optalysys, we're building the hardware acceleration layers that solves that problem and unlocks the future of blockchain and Web3. So one of the key features of blockchain is its transparency. This has also become its biggest hurdle. So data that is publicly visible on the chain is no good for commercially sensitive data being placed on there. Enterprise organizations cannot deploy applications, and in DeFi, users are losing billions from attacks such as MEV and front-running issues, sandwich attacks, because the transactions are always public. As Jeremy Allaire of Circle put it, the biggest barrier to widespread enterprise adoption of blockchain is privacy. To onboard the next billion users and unlock trillions in value, we have to move beyond a fully transparent model. We need practical on-chain privacy. The solution for this is a set of cryptographic schemes known under the banner as fully homomorphic encryption, or FHE. Where conventional cryptography allows data to be protected whilst at rest or in transit, FHE is fundamentally different. It provides the ability to process data while still encrypted. Some believe it's the cryptographic holy grail and solves the challenges around how data is used and made confidential on the blockchain and many other applications besides. In terms of use cases, so we can look at MEV-resistant DeFi, truly private DEXs with encrypted order books, secure governance, secure on-chain gaming with private asset attributes and confidential logic execution, enterprise compliance, so a number of regulations including GDPR and DORA protecting commercially sensitive data which are legally bound these days as well. Private digital identities, verifying without revealing sensitive personal data. So with the arrival of these solutions and tools for creating and working FHE in blockchain, the opportunity to realize the potential of these technologies is now here. However, achieving the full scope of what confidential blockchain has to offer is very much contingent on the ability to handle encrypted operations at scale. And it's only through the orders of magnitude speedups provided by dedicated hardware acceleration that the most transformative FHE-powered use cases can drive the next wave of blockchain revolution. And that revolution starts here. Today we're introducing our LightLocker node. This is the world's first dedicated enterprise-grade FHE solution for blockchain. It's an FPGA-based solution, purpose-built to execute the core mathematics of FHE at speed. In the case of our LLN 1300 model, we're using AMD V80 FPGAs designed for high performance and flexibility. These unlock scalable encrypted computation and will be updated regularly in line with our technology roadmap I'll tell you about in a moment. We look to support additional FHE schemes, blockchain infrastructure, additional chains, all the while increasing performance of the actual processing. We've deployed our own FHE VM architecture from Zama, starting with our own Ethereum testnet that we've now launched, deployed to the cloud. We put the rest of Zama's FHE components in the threshold key management system, wrapping that up around a coprocessor unit. And this means we can benchmark the whole operation from start to finish. So in terms of a demonstration, we have a testnet open to new users. We've put together some simple applications here. So in this case, we have two people logged onto our DApp on our testnet, one being Alice, one being Bob. Alice's address starting 49, Bob's address starting B0. Both have encrypted balances. So first we're going to decrypt those balances. Alice confirms the request. You can see that her balance is 50. We do the same for Bob, decrypt his balance, confirm the request. You can see Bob's balance is also 50. Now, Bob's going to send 10 tokens to Alice. We encrypt the amount, so that's encrypted with the zero knowledge proof. We enter Alice's address, paste that here, and we want to transfer the encrypted amount to the receiver. So we hit the transfer, confirm the transaction request. You can see that the encrypted balance has changed, so the transfer has successfully gone through. Now, if we refresh Alice's DApp, we can see that she now has an encrypted balance. Decrypting that shows the balance is now 60. Go back to Bob's to decrypt his balance, confirm that's 40. So we've successfully transferred 10 tokens from Bob to Alice under a fully encrypted scheme. So at no point has the data been exposed through that process. So on a real system, any volume of transactions, for any volume of transactions, you'll have multiple transactions coming in at random times. So the key figure here is system latency. For a blockchain end user, that's the time lag between clicking their mouse and a transaction completing. For a blockchain infrastructure operator, it's the time for the chain to reach consensus. And that's in reality made up of several different contributions. Primarily, it's a combination of the single transaction latency and the throughput of the system. That's how many transactions per second can be performed on a sustained basis. So user perceived or system latency is much more important than single transaction latency that's sometimes quoted. To optimize that, we have to care about throughput and latency. So it's worth noting that on an engineering level, single transaction latency and throughput are somewhat conflicting. This graph shows the performance of the LightLocker node against a roughly equivalent GPU-based system based on NVIDIA H100s. This gives a fair comparison on the basis of cost and power consumption. Here we're looking at how long it takes to execute a batch of transactions on each system. So the LightLocker is the grey line, the GPU system is the green. As you can see, the two systems have comparable initial latencies, around 400 to 500 milliseconds, but beyond the first 20 or so transactions, you can see that the LightLocker node rapidly outstrips the GPU-based system in terms of actual results. And the story gets better as the throughput advantage becomes more prominent. You can see here that by the time the systems have been running for 10 seconds, our node has already processed around twice as many as the GPU-based system. So to help you understand what configuration you're going to need when you've developed a tool such as this, you can select your smart contract, upload your own smart contract to our code, our tool, set your target performance and the network architecture. We put in the smart contract, the function we want to process, the performance level required, the network architecture, in this case an optimistic rollup, and put this number of standby nodes in, and you'll see that with the model of the LightLocker node we have here, you need 2 servers per coprocessor to get performance over 200 transactions per second. So in this case, we need 2 of our servers. So you can use that tool on our desk. You'll talk about it at our stand in the WAGMI area in a moment. What we are doing here is we're making FHE practical for the blockchain ecosystem. Now, but to power a global encrypted internet and handle immense workloads in the future, looking at further applications such as Web3 and other and secure AI applications at a global scale, we have to push beyond the limits of where electronics gets us. The ultimate bottleneck becomes the energy and the time it takes to move electrons, and that's why a core development at Optalysys is not using electrons. We use photons, so we compute with light. So by doing that, our future optical accelerators unlock further orders of magnitude gains in speed and power efficiency. This isn't just about faster FHE, it's about building a fundamentally new class of compute infrastructure, capable of powering a truly secure and private global web. So the route to mainstream blockchain adoption becomes clear. It begins with the need for confidentiality enabled by FHE. If we come back to our friend Jeremy Allaire again at Circle, who says, no business in their right mind is going to build on-chain unless they have totally secure confidential transactions. So if we want society at large to adapt blockchain technology, we have to preserve the privacy of the data. It's made practical today with our Gen 1 light locker node based on FPGAs, and we scale that into high-performance future technology with our photonic solutions, pioneering advances in optical computing. So if you're building the future of blockchain and need practical high-speed confidentiality, then come and talk to us. You can visit us at our stand in the WAGMI Boulevard. Use the tool that we went through live, chat through use cases, and also catch us at the Phoenix Encryption Day on Thursday at the Hotel Grade Albion. You can also scan the QR code here, find out more about us and the Light Locker node, and download documentation. Thank you very much. Any questions?
Any questions, guys?
Yeah, my question is, how much is the photon chips are expensive? I mean, can normal users can afford it?
So price to be determined. These are still under development at the moment. We are not aiming them to be prohibitively expensive, though, and in fact, part of the features of photonics is the ability to actually use processors that aren't necessarily expensive to build with. So this is going to be comparable in terms of GPU costs. What we're aiming for is widespread adoption of this technology. So more news to come on that.
All right, thank you.
Okay, thank you.